Hello and welcome to our next lecture in CHY 113. Last time we talked a lot about thermochemical equations and how we can find the energy that's associated with a chemical reaction. Where we left off was discussing the use of calorimetry and how we can use calorimetry to directly measure the energy of a reaction. And if you recall, we typically do that, the essence of how we do that is that we can run a reaction in water, and then that reaction is going to transfer energy, either release energy into the water or take energy from the water. And we're able to then calculate the amount of energy change of the water because we know the mass of the water, we know the specific heat capacity of water, and we know the temperature change of the water. And so we can measure the energy change of the water, and then we know that the energy change of the reaction had to have been equal and opposite to the energy change of the water. Law of conservation of energy tells us so. And so that gives us a way for nicely controlled reactions that we can run in water and measure the energy change directly that way. That works great for lots of different reactions and lots of different processes. There are several reactions, though, or lots of reactions, where we can't control them. Maybe once the product is made, that product immediately goes on to react with something else, or that product immediately decomposes, or there's a side reaction that occurs. There could be any number of things that would make it so we can't run that reaction directly or measure that reaction directly. And so that's where we're going to focus today, is what we can do to find the thermochemical information about reactions that we can't measure directly by something like calorimetry. And so in order to look at some of the concepts we're going to look at today, we need to discuss something that we call state functions. The actual definition of a state function is that it's a property of a system that is determined by the state or the condition of the system, not by how it gets to that state. The value is fixed when temperature, pressure, composition, and physical form are specified. U and H, overall energy, and enthalpy are state functions. Now, what this really means is, well, let's look at an example. I think it might clear it up a little bit. And so a state function means that the overall function, the overall system that we're looking at is going to be the same regardless of how you get there, regardless of the path you take to get there. And so, for instance, if we look at the distance from Dayton to Los Angeles, so we have that straight distance. That distance doesn't change no matter if we go there directly or if we have several layovers, as would probably be the case if we were really making this flight. So we could go Dayton to Atlanta, to Salt Lake City, to San Fran, and then to LA. So we could take a very circuitous, very circular type route, or a very complicated type route to get there. But that doesn't change the overall distance. Once we're in LA, the path that we took to get there doesn't change the distance that we are now from Dayton. That distance is still the same. So that distance between Dayton and LA, that's a state function. That distance will be exactly the same no matter our pathway to get there. Things like change in latitude or change in elevation, same exact idea. If let's say that I am going up over a mountain, I'm going from one side of the mountain over to the other, I could either go directly up over the entire peak, or I could go up, take a peak bypass trail, and then down. Either way, I'm getting from point A on one side to point B on the other side. The path that I take to get there is going to be different, but where I actually end up is going to be the exact same. We're going to apply that to energy equations. We're going to apply the idea of state functions to energy equations, because what this enables us to do is it allows us to apply lab measurements to real life situations. And so, in other words, if we want a reaction A goes to B, whatever A might be and whatever B might be, we want a reaction of A goes to B. but we can't measure A to B directly. We can, though, possibly measure A to C, and we can measure C to D. So that overall energy, if we know the energy from A to C and from C to D, those energies combined are going to be equal to the energy from A to B. Again, it doesn't matter the pathway that we take to get there. We could go through 7 different reactions in order to get from A to B. And as long as we can measure the energy of all those, that will be equal to the energy difference from A to B. And so we can measure the enthalpy of a reaction indirectly by using the enthalpy of the steps that lead us to that same reaction. That is the very essence of what we call Hess's law. Hess's law states that if a reaction is carried out in a series of steps, delta H for that reaction will be equal to the sum of the enthalpy changes of the individual steps. And again, this is incredibly useful for reactions in which we cannot measure the enthalpy directly. So let's take a look at an example of this. Let's take a look at why we might need to do something like this. So in this example, we want the energy, we want the enthalpy of this particular reaction, of the formation of 1 mole of carbon monoxide from its constituent elements. And so carbon plus half O2 to give us CO. So that's the reaction that we want energy information for. The problem is that carbon monoxide immediately reacts with O2 that's still present to then form CO2. And so there's no way for us to just stop the reaction right here, right when carbon monoxide is made, to then just stop it and measure the energy. We can't do that. That carbon monoxide is immediately going to react to form the more stable carbon dioxide. And so we cannot simply measure the enthalpy of this reaction. We do have a couple similar reactions, however, that we do know the enthalpy for. We know the enthalpy for the reaction that happens after this one, for CO plus half O2 to form our CO2. So the reaction that occurs after CO is formed, we know the enthalpy for that. We also know the enthalpy for directly forming carbon dioxide from carbon and oxygen. So carbon plus O2 gives us CO2, and we know the enthalpy of that reaction. So we know 2 related enthalpies, but we don't know the enthalpy of the reaction that we're looking for. And so to just recap, this is the reaction that we want our energy information for. We want the energy information for carbon plus half O2 gives us carbon monoxide. The reactions that we have energy information for, though, are carbon monoxide plus half O2 to give us CO2, and also carbon plus O2 gives us CO2. So we have the information for those reactions. This slide doesn't help us much. Let's look at a diagram. So I think this will help to sort of start to drive this home. So you can see that this is the actual process that we want our energy information for. It looks a little bit different. I know that's because we're written in reverse here. Or sorry, let me back up. If we look at this reaction here, so carbon plus oxygen gives us carbon monoxide plus half O2. That looks slightly different from the reaction that we were looking for, but it really isn't when you really dissect this. So let's just take a look at something real quick, because this is going to be something that we have to use and think about with Hess's law. So remember, the reaction that we want any energy information for is carbon plus half O2 to give us CO. So this is the reaction that we want our energy information for. If we look at just this pathway right here, so carbon plus O2 gives us CO plus half O2, we really see that we can sort of reduce that. If we just sort of think about the net reaction here, if we think about the totality of what's going on, we start with 1 O2, we still have half an O2 at the end. Now remember, this is moles, so we can have half of a mole easy enough. So we start with 1 mole of O2, we end with half a mole of O2. So realistically, we're only using half a mole of O2 here. And so if we're only using half a mole of O2, let's just write the equation that way. And we can see that that is the reaction. We come back to what we were looking for. That's the reaction that we want our energy information for. So I just show you that sort of side, just to show you that realistically, in this energy diagram here, this reaction pathway right here, C plus O2, gives us CO plus half O2. This is the energy pathway that we are looking for. This is the information that we want. However, remember, we don't have information for that particular reaction. We have these related reactions. We know the energy of carbon plus O2 gives us CO2. Sorry, I'll wait for that to disappear. There we go. See if I can fix it. Okay. So C plus O2 gives us CO2. So we have the energy information for this reaction. We also have the energy information for this reaction. For carbon monoxide plus half O2 gives us CO2. So we know the delta H of that. So we have the delta H's of both of those different reactions. We have the reaction, full reaction right here, and we know the information for this reaction right here. And so what we want, though, again, is this pathway right here. So remember, what a state function is, or what a state function tells us, is that if we want to go from here to here, it doesn't matter how we get there as far as the energy is concerned. We can either go directly, or if we did this, if we took that route, if we did those two steps instead, first this reaction and then this reaction, that still gets us there. We're starting from the same point, we're ending at the same point. And so since enthalpy is a state function, it doesn't matter if we take this longer route to get there, that energy difference is still going to be the same. And so the quantity of the heat is independent of the path that we take to get there. The only thing that we have to note and remember is that, remember, when we reverse a reaction, we reverse the enthalpy difference. And so we have the enthalpy of this forward reaction going this way is negative 283.0 kilojoules. That just means that our energy difference going the other way, if we're going from CO2 to CO plus half O2, that energy difference is going to be positive 283. And so if we're going this route here, this first energy difference, negative 393.5, and then plus 283, gives us an overall energy difference in this equation of negative 110.5. That's Hess's law. It's using information that we have to get to where we actually want to be. The quantity of the heat is independent of the path that we actually take to get there. And so this showed us what it looks like in diagram form. Let's take a look at what this would look like if we're performing a Hess's law problem, so to speak. Okay, so just a reminder, back to what we were looking at before. This is the information that we've got. We know the enthalpies of these two different reactions here. And so when you're setting up a Hess's law problem, what I would do is I would set up those equations like so, write out those equations with the energy differences, but leave some space in here because we might need to manipulate these equations a little bit. I usually then put a line down underneath, again, leaving some space right in here. We want to leave a little bit of room in here because of some reasons that we'll see in a little bit when we start to manipulate our equations. Lastly, I would then put my target equation, what I'm looking for, down below the line. And that's the enthalpy that I'm looking for. And so when you're doing a Hess's law problem, what we now want to do is manipulate our two given equations however we have to, so that what we're left with is what we're looking for in our target equation. When we start to manipulate our equations here, the equations that we're given, we want to manipulate them in such a way that up here we have all reactants in our target over on our reactant side, and we have all products in our target over on the product side, and anything that does not appear in our target equation must cancel out of our given equations. And so, for instance, we see quickly that CO2 appears up here in our given equations, but CO2 is nowhere in our target equation. So that means as we manipulate these two equations up here, we're going to need to manipulate them in such a way that carbon dioxide is in the reactant side of one and in the product side of another, so that they effectively cancel each other out. And so when we start to look at these, at how we want to manipulate these equations, keeping all of that in mind, keeping in mind that we need to get everything that we're looking for, our products and reactants, on the proper side, and everything we don't need needs to cancel out. With those in mind, let's take a look at these equations. So we see that we need carbon over here in our reactant side. And so we look in our given equations. Carbon's nowhere here, but we do have carbon in our second equation, and it's in the reactant side. So that's good. That's one of the things that we're looking for. O2 we'll leave and we'll save for the end, but so far we're looking okay because we do have some O2. We're looking for it as a reactant, and it does show up as reactants in both of these. Tells us we might need to play with that a little bit, or we'll see what happens after we manipulate some other things. We need carbon monoxide. We need CO as a product, but CO is up here as a reactant. So that tells us that we need to flip this equation around. We need to flip this equation so that CO ends up over on the product side. I find it helpful when I'm doing these, even when I'm doing them out on paper. You can see I've got an example here. When I flip or when I manipulate, to write in a different color. That's just me as I'm going through the process, but I find that easier to keep track of what I'm doing. And so I flip this equation. Now I get CO2 gas gives us CO plus half O2. Now remember, when I flip an equation, that means I have to flip my enthalpy. I have to change my sign of my enthalpy. So delta H now is going to equal positive 283 kilojoules. I would then go ahead and cross this one right out. Cross that whole thing out so that you don't get confused with it later on. We know that we're not going to need that because we've manipulated the equation in the way that we need. And so let's just kind of take stock of things a little bit and see where we're at. We have carbon. We're looking for it in the reactant side. We have it here in the reactant side. That's perfect. That's exactly what we're looking for. CO is in our product side. That's exactly what we're looking for. So that's great. CO2 shows up as a reactant here and a product here, so we can cancel those. So that's awesome because we don't want CO2 anywhere in our final equation. And so let's now just take a peek at the O2. We have 1 mole of O2 as a reactant, and we have half of a mole of O2 as a product. And so that realistically means that what we can also do is sort of reduce that down. And that leaves us with half O2 there. And half O2, which is what we're looking for in our final equation. So that's perfect. That means that we're now at a point where we have manipulated all of the equations in the way that we need for everything to work out. And so now we simply add up the enthalpies that we are left with. And so we're going to take 283 positive minus 393.5. Sure enough, that leaves us with an enthalpy of Erase our question mark because we have a final number for it now. We have an enthalpy of negative 110.5 kilojoules, which, if you will recall, was exactly what we found. And so that shows us how we go about Hess's law questions. And so the general, your general pathway, your general problem-solving approach to these problems is, first you want to manipulate your equations in whatever way that you have to in order to get your products where you need them and your reactants where you need them, in order to get things to cancel out. Manipulate them however you have to. And then add and subtract any reactants and products. If something shows up on the reactant side and on the product side, subtract them and cancel them out. If you have maybe 2 of a particular particular compound on the reactant side and 4 of that compound on the product side, then okay, simplify it, get rid of it on the reactant side, you're left with 2 on the product side. And so do any of that simplifying down. Remember, whatever you do to the reactants and the products, you have to do the same thing to the delta H value. And so if you flip your reaction, you have to flip your delta H value. You may find in some cases that you need to multiply a reaction through by a certain number. Maybe your target equation, let's just look at a rough example here of what I'm talking about. Let's say that in your target equation, so maybe we want 2A plus B gives us C. And if we look in some of the reactions that we're given, maybe we're given an A plus D, give us an E over here. Maybe that's got a delta H value of 100 kilojoules, just as an example. And so we can see that we actually need 2A, we need 2 moles of A in our target. We're only given 1 mole of A in our given equations. And so in that case, we're just going to double our equation here. 2A plus 2D give us 2E. And so we're then going to double our delta H value there. And so if we just sort of continued this, let's say maybe another one of the other reaction that we had perhaps was maybe, so let's say that the other reaction maybe that we had information for was C goes to 2E plus B. And we knew the delta H of that to be maybe negative 150. So again, we could see that from in this equation, we want C as a product, so we're going to have to flip this one. So we go ahead and do that. We flip this equation to get 2E plus B gives us C. We flipped it, so that means we're going to reverse our enthalpy. Cross that one out. And then we go through and we look at everything that we've done. 2A in our reactant side, so that's good, we're looking for that. B in our reactant side, so that's good, we're looking for that. C on our product side now, so that's good. Our 2E cancels out, so we have 2E in our reactant side and 2E in our product side. So we've done all the equation manipulating that we have to do. So we would finally just add these up, and our target would have a positive enthalpy of 350 kilojoules. And so again, you go through and you do all of your equation manipulating first. So anything that you need to, sorry about that. Anything that you need to manipulate in your equations, do so that you end up with what you want in your target for a reactant and product. You end up with those in the right places. Everything extra cancels out. And then finally, worry about the actual calculation. Worry about the actual calculating of enthalpy until the very last. You'll notice in these two examples that I've done, I didn't worry of anything at all about my final enthalpy calculation until after I'd done my manipulations, after I knew everything canceled out that needed it to. At that point, I said, okay, now I've manipulated my equations in the way that I need to. It means that I've manipulated my enthalpies how I needed to. Now I just add them up. This is not necessarily easy or intuitive stuff. It is okay if you're sitting there at this point in the lecture going, what? That is absolutely fine, to be expected with some of these problems. These are complicated problems and require a way of thinking maybe that you're not used to. And so I just say that so that I can tell you to rest easy, relax. If you're a little bit confused and lost right now still, that's okay. We're going to look through some examples right now. We're going to spend a good deal of the rest of this lecture just going through some examples. And then you're hopefully going to do a lot of practice problems on your own as well. And it'll start to click in and gel a little bit. So if you're still a little bit sort of confused about what's going on, that's okay. We're going to go through some examples and you're going to be fine. And so first, so again, so we can see sort of our general Hess's law setup, that our target equation is down here. We can see here, we just want to know the enthalpy change that's associated with a phase change of our energy, of our 2 moles of water going from the gaseous phase to the liquid phase. What is our enthalpy change of that? And we can see the information that we have. We have 2H2 gas plus O2 gas gives us 2H2O gas. So we know the enthalpy change of that. We also know the enthalpy change of 2H2 gas plus O2 gas gives us 2H2O liquid. So we have those 2 enthalpy changes. But what we're looking for is this pathway here. And so we can see one of the things that we first see right away is that H2O gas we want as a reactant, but H2O gas is a product in our given equation. And so let's flip it. So we're going to flip that one around. It means that we're going to reverse the enthalpy of that reaction as well. So we flipped it, we reverse our enthalpy. So now let's go ahead and just cross that equation out and not even think about it anymore. And now let's just sort of take stock of where we're at. And so we can see that we have 2H2 now as both a product in equation 1 and a reactant in equation 2. So let's cross those right out. Those are going to disappear. We're not going to think about those anymore. We can see that we also have O2 as a product in equation 1 and a reactant in equation 2. So those are going to go away. And we can see that once we do that, we have what we're looking for. We have 2H2O gas as a reactant, which is what we're looking for in our target equation. 2H2O liquid as a product, which is also what we're looking for. So that tells us that, and we have nothing left over. We have nothing else up here that we have to worry about. It tells us we've done all the manipulating of any equations that we need. And so that means that we've manipulated our enthalpies in the way that we need. And so now we just add them up. Positive 483.6 plus a negative 571.7 leaves us with a delta H of negative 88.1 kilojoules. Let's look at another example. So here our target equation is zinc carbonate decomposes to form zinc oxide and carbon dioxide. So if you remember back from a while ago now when we were looking at equations, that's what carbonates do. Metal carbonates will almost immediately decompose to form the metal oxide and carbon dioxide gas. And so now we're just looking at the energy change associated with that. Now we have 3 equations to work with instead of 2. Same exact idea. We're going to go through the same exact process. We just have more equations to work with. And so we have our target equations here. So let's just sort of start dissecting where we're at and what we need. One of the things that we see is that zinc oxide we want as a product, but zinc oxide shows up as a reactant in our given equations. So we'll start by flipping that. So we're going to flip that one over and sorry, and that means that we flip the enthalpy as well. Sorry, it disappeared down here. I'm not sure where it went, but our target equation is still at the top here. So we've flipped this and we've flipped our enthalpy. Another thing that we notice is our zinc carbonate we want as a reactant, but it's in our equations as a product. So we'll go ahead and flip that one as well. So we're going to flip that one and we're going to reverse our enthalpy. And so let's take a look and maybe see where we're at this point. We can see that we have H2CO3 and H2CO3 as a reactant and as a product. So that could be crossed out. H2O as a product here and as a product here. So we have two H2Os as products and we have two H2Os as reactants. So that can disappear. We also have a zinc hydroxide as a reactant and a zinc hydroxide as a product. And so if we cross all of those things out and then look at what we have left, is exactly what we're looking for. Zinc carbonate as a reactant, zinc oxide and carbon dioxide as our products, and so then we can add up our enthalpies. And so I would actually encourage you to go back and do this, both the examples that we've done, but I would go ahead and I would start from right here, write this out, and see if you can manipulate these. See if you can do what we just did. It's still fresh in your head, so hopefully it's familiar, but doing it again on paper yourself will really help embed this concept and help you to really start to learn it. And so start from here, start from our beginning, and then see if you're able to come up with our 17 kilojoules. Another example here. So here we want to look at the combustion of 1 mole of C2H2. And so we have our target equation up here, our 3 given equations down below. And so let's start to take a peek at this. We can see that in our first equation, for instance, we have our C2H2 as a product, but we're going to need it as a reactant. Tells us that we're probably going to want to flip that equation around. We also notice, we also notice something that might not be quite as obvious as you're just looking at this to start out. But if we look at our numbers of O2 that we're going to need, we can see that we're going to want 5/2 O2 in our target equation. And so let's just take a look at where O2 is in our given equations. We have O2 as a reactant here and as a reactant here. And those are the only places that O2 is showing up in our given equations. So that tells us that if we flip this middle equation, if we flip this one around and we end up with half O2 over here and 7/2 on this side, and we also multiply this one through by 2, then that would get us to where we need. So again, I know that's a little bit confusing, but if we multiply this through by 2, that gives us a full O2. Then we flip it, and that would give us then what we need to get down to our 5/2. Let's just take a look at that. So see how that works out. Sorry, the color didn't change there. I should fix that in my slides. But what we've done now is flipped this equation so that we end up with 1 O2, because now we can take our 1 O2 here on our product side and our 7/2 O2, and that would get us to our 5/2 of O2 that we need here. And if we look at some of the other aspects, another reason that we had to multiply this one through by 2 was to get our H2s to cancel out, as well as to get our H2Os to add up to what we needed, because we need to end with 1 H2O, and in our given equations, we have 3 in our product side. And so doubling this one after flipping it gave us 2 on our reactant side, so those will cancel out again to just leave us with 1. And so now if we look at everything that we can cancel. So again, if you don't believe me, go through and check those. But we see that our 7 halves canceled down to 502, 5 halves 02. Tells us that we've canceled everything that we needed. We've manipulated everything that we need to do. So now we can just add up our enthalpies and get to negative 564 kilojoules. Again, I highly encourage you with this one to go back to the beginning, do the manipulations, write them out, and make sure that you're able to come up with our negative 564. So let's look at yet another example. Only instead of doing this one out on the computer, we're going to go ahead and just write it out as if you were setting this problem up yourself. And so we're going to rewrite this information here. Let's just shrink this down. And so I would start, again, when I'm doing these problems, what I would do is start out with your given information, start writing that out. So we have carbon, should leave our states of matter in there, carbon plus O2 gives us CO2. So we have one equation. Let's just get these written out here. And finally, our third. Leave a little bit of space and then write in our target equation. There. And so that's just rewriting all our information in a way that we can now work the problem. And so a couple things that stand out to me as I look through this, some things that I start to notice, is that I see, first, if I look at our first given equation, I see carbon dioxide, 1 mole of carbon dioxide as a product, 1 mole of carbon dioxide as a product in our target equation. So that tells us that for now, we don't want to touch our first equation because that has things the way that we need. If we start to look at our second equation, one of the things that we notice is we have 1 mole of SO2 as a product. We need 2 moles of SO2 as a product in our target equation. So let's go ahead and just go through that equation and double it. So we're going to have 2 sulfurs plus 2 O2s giving us 2 moles of SO2. Means we need to double our delta H. It's negative 593.6. And so then let's go ahead and just cross this one right out. And then if I look at our last given equation, the thing that stands out to me right away is that I have CS2 as a product, but I'm going to need CS2 as a reactant in my target equation. So let's go ahead and just flip this. Let's flip this equation right around, and we're going to instead get CS2 gives us C plus 2S. And we've flipped that, so we're going to change the sign of our enthalpy. And then we're going to go ahead and cross this right out. And so now it looks like we might have taken care of everything that we need, but let's double check. And so we can start to look at things that can cancel out. We have carbon as a reactant, carbon as a product, so that can disappear. We have 2 sulfur as a reactant and 2 sulfur as a product, and so that can disappear. And now let's look at everything that we have left. We have 1 O2 as a reactant and 2 O2s as a reactant. So that adds up to our 3 O2s. So that's good. CS2 here as a reactant, CS2 here as a reactant. So far, so good. CO2 as a product, CO2 as a product. 2 SO2 as a product, 2 SO2 as a product. Tells us that we've done all the manipulations that we need. We can now finally just add up our enthalpies. And so negative 393.5 plus a negative 593.6 plus a negative 87.9 give us a final enthalpy of this reaction of negative 1,075 kilojoules. And there we have it. We've done all the manipulating that we need, so we just add them up. And so now a couple examples that I want you to just work out on your own. And so just like we've done in the past, I would absolutely encourage you to pause the video at this point. Pause it and work this problem. If you haven't been doing that as we've been working in some of our other lectures, I highly, highly, highly encourage you to do this. This is the way that you will learn. It is the way that you will start to learn how to do problems like this. If you actually work them while they're fresh in your head through a lecture. If this were a live lecture, absolutely, I would be giving you time in class. I would let you get out some paper, and I would give you a few minutes to work this problem. And so do that. Pause the video, work this through, see if you can come up with the same answer that I have. So pause the video now. Okay. So hopefully you were able to come up with an answer for this question, a final answer of positive 175 kilojoules. And now another example. So now we have the combustion of C3h6o. And so same thing. Pause the video at this point. Pause the video, work this problem. And so pause the video now. And hopefully you were able to come up with an answer of negative 1361 kilojoules. And one more for you to work on your own. Here we have the reaction of thermite, very fun, very energetic reaction. So we have our target equation at the top. We have our 2 given bits of information. And so again, pause the video now and work through this problem. And hopefully you got negative 847.6 kilojoules. And so that's Hess's law. Hess's law is, again, it's a method that we can use to find the energy of a reaction if we're not able to measure the energy of that reaction directly. There's another way that we can do this too. If we, again, don't have the information for a reaction directly, but we do have what are called the heats of formation of all of the compounds that are involved in the reaction, the enthalpies of formation. The enthalpy of formation of any compound is the amount of heat that is required to form 1 mole of that compound in its standard state. And so, in basic terms, it's just how much energy does it take to make this compound. And standard state are just the standard states that you would normally think of. And so something like if you're making, that you normally think of at room temperature. Or even, sorry, not even necessarily at room temperature, because you might have some other information about that, maybe that, sorry, I know I'm saying this very poorly. Let's look at an example. And so let's say, for instance, that we wanted to find the enthalpy, or we were looking at the enthalpy of formation of H2O liquid. And so that would be starting with, so from its standard elements, so H2 would exist as a gas at room temperature, plus O2 exists as a gas for the formation of H2O as a liquid. And so we're only looking at the formation of 1 mole of H2O, so we would have to go with half O2. And we in fact have enthalpy of formation for H2O liquid at negative 285.8. And so our delta H of formation for this, negative 285.8. And so that's all enthalpy of formation is. It's just how much energy does it take to make a particular compound from its elements. And these are just several different examples here. The enthalpy of formation for an element in its standard state is 0. And so that's going to be something that's important for us to know. And so, for instance, if we were looking, so H2 that we saw in the previous example, H2 exists as a gas at room temperature. And so if we were looking for the standard enthalpy of formation of H2, that standard enthalpy formation is going to be 0. And so that's just good to know, because we're going to be using these heats of formation in calculations. And so you'll just need to know that whenever you see anything in its standard state, whenever you see the enthalpy of formation of H2 or the enthalpy of formation of O2, something like that, it's going to be 0. Most delta H values, delta heats of formation, are negative, indicating that formation from the elements is a negative process, that it releases energy. And we can use the delta heat of formation can be used to compare what we call the thermal stability of related compounds. And so, for instance, HF, the formation of HF releases energy, but the formation of HI actually takes energy, which is fairly uncommon. And so that tells us, so whichever compound is more negative is going to be the more stable compound. The releasing of more energy leads to more stability for a compound. And so just try some of these. Just go ahead and write out the thermochemical equation, which would represent the standard enthalpy of formation of these compounds, just to make sure, again, that you understand what enthalpy of formation is. For example, though, if we're looking like at NaCl, let's do that one out for you. So we're looking for the formation of NaCl from its elements. So we would have, and they'd be elements in the standard conditions that you would think of them. So Cl2, which would be in the gas form, but it's Cl2, and we see that we only need 1 Cl in our product, and so we would go with a half a Cl. So Na plus half Cl gives us NaCl. So this would be the equation that represents the formation of NaCl. Now, the way that we are going to use this, though, is that the delta H of a reaction, the enthalpy of a reaction, is going to equal the sum of, if you haven't seen this symbol yet in science or in math, it's just an uppercase Greek letter sigma. And so it just means the sum of the enthalpies of the products minus the enthalpies of the reactants. So to find the heat of formation of a reaction, take the heat of formation of the products minus the heat of formation of all the reactants and subtract. You also have to take into account the number of moles from our balanced equation. And so we'll see what we mean by that in just a second. So let's look at an example, because I know this is getting kind of wordy and it might be tough to visualize. Let's really look at one. So we want to know the heat of formation of glucose. So we're going to calculate the delta H for the combustion of glucose. Or this is a way that we would use this. And so we want to know the heat of combustion of this reaction here. We want to know the energy associated with this reaction. we have all this information. We have the heats of formation of glucose, the heat of formation of CO2, and the heat of formation of H2O. Now remember, we don't need the heat of formation of O2 because the heat of formation of this compound is 0 because it's an element in its natural state. So the first thing that we have to recognize is that this equation is not balanced. And so we're going to balance it first. I'm not sure what's happening with my slides, but now we've balanced this equation. So that's going to be key for us. And so what we want to do now is take all the heats of formation of all of our products and subtract the heats of formation of our reactants. And so let's take a look at that. And so it might help to even just sometimes write that out, that we're going to do products minus our reactants. And so that means that we want, so for our products, let's just sort of write out what they are. We're going to look at the heat of formation of CO2 plus the heat of formation of water minus our reactants. And you don't have to write all of these out when you're doing these problems. I'm just sort of showing you what it would look like. And so it's our CO2 plus our H2O. Those are our products minus the sum of our reactants. And we have values for these. And so for CO2, we have a value of negative 393.5. But again, we need to take into account how many moles are in our balanced chemical equation. So we're going to have 6 times that negative 393.5 plus our heat of formation of water, 6 times negative 285.8. So there's the heat of formation total of our products. We're going to subtract our reactants. We look on the table for our value of glucose, negative 1274.5. We have 6 O2s, but that gets a value of 0. And so there's our setup. So we go through and we do our math here. We add those up, and we get a value of negative 2801 kilojoules per mole. And so it's products minus reactants. That's all it is when you're using the heats of formation. Add up the heats of formation of all of the products, taking the number of moles into account, and then subtract the heats of formation of all of the reactants. Be very, very careful about your signs here. You can see pretty quickly that if you forget one negative sign, you're done. That's going to throw your whole answer off. So be very, very particular about making sure that you have negative signs where you need them and that you're carrying that through with the math as you do it. Let's look at one more example. So here, we want to actually calculate the standard enthalpy of formation of octane. So here we're trying to calculate our delta HF of a particular compound. We are given the heat of combustion of octane. So we're told the overall energy of this reaction. We're going to use that. And so ultimately what we want to calculate our delta HF of this compound right here of octane. We're given the heat of combustion of octane. And so the first thing that I would do is write out that equation. The combustion of octane, so C6H18. Sorry, I just realized there's a major typo in here. I'm going to fix that right now while I am thinking of it. I'm sure none of you caught that, or maybe a couple of you did. When you go on to OChem, you will have definitely caught it. Octane is C8H18, not C6. So now that we've fixed that, fixed it here. So C8H18. So we're looking for the combustion of this compound. Remember, combustion reactions will always involve oxygen. And the product of all combustion reactions of hydrocarbons, the products are always CO2 plus H2O. I'm sorry, I didn't leave myself enough room here. So let me actually rewrite this whole thing, making sure that I am leaving myself enough base. Shrink this down a little bit more. And so again, we are given the delta H of this whole reaction. We're told that the heat of combustion of octane, that's this reaction right here. So the heat of combustion of this reaction equals negative 5440 kilojoules. So we know the heat of combustion of this reaction. What we're ultimately looking for here, what we want to know, is the enthalpy of formation of our C8H18. We want to know the delta HF of this compound right here. And so the first thing that we're going to want to do is definitely balance this equation. And so when we go through and balance this, we can see that we're going to need 8 CO2s to get us our 8 carbons. We're going to need 9 H2Os to get us our 18 hydrogens. That leaves us with 25 oxygens on our product side. We have O2 here. So we're going to go with 25 halves O2. Now remember, like we talked about a couple lectures ago, when we're writing out a thermochemical equation like this, it is okay to have fractional coefficients. We need this one to have a fractional coefficient because we're given energy information. This 5440, negative 5440, is for the combustion of 1 mole of our octane. And so the only way to keep this at 1 mole is to have my 25 halves O2 here. So just a side note to remember that in a thermochemical equation, it is okay to have fractional coefficients. And so let's take a look then at what we want to do here. So remember that when we're looking at heats of formation, remember we said that the delta H of a reaction is going to be equal to the sum of the delta HF of our products minus the sum of the delta HF of our reactants. And so let's start putting some of those numbers in. We know the delta H of this reaction. We were given that to start out with. We were told that the delta H of this reaction is negative 5440. I'm just going to leave the units out for now, just to make it a little easier to see. So the delta H of this reaction is negative 5440. So now let's start looking at the delta HF of our products. We have 8 carbon dioxides. We look on our table. We see negative 393.5 for the formation of carbon dioxide. And we're going to add in our water. We have 9 waters. Negative 285.8. So there's the delta HF of our products. We're going to subtract. Running out of room. Hope it doesn't get too confusing if I write it down below. But we'll subtract. Actually, I don't need to. We'll see why. Sorry, talking to myself a little bit. But from that, we're going to subtract the delta HF of our products. One of those is what we're looking for. So I'm just going to leave that in here as C8H18. That's ultimately what we want. We want the delta HF of our C8H18. And then plus our 25 halves times the delta HF of O2, but there's an element in its natural state, and so that's going to be 0. And so there's our setup there. And so now we can start to do out the math of this. Negative 5440 is going to equal, when we do the math of this in here, we're going to get negative 3148 plus a negative 2572.2 minus our C8H18. And so again, we just carry through our math. If we add the delta HF of CH18 to both sides, add 5440 to both sides. Just look through the algebra, make sure for yourself that that works out. But then we do that out and we get a final number of negative 280.2 kilojoules per mole, which is our delta HF of octane. And there it is. And that's it. That is all for today. And so just a quick recap that what we have looked at today is how we can find the thermochemical information, how we can find the energy involved in a chemical reaction if we cannot measure it directly. So we've looked at two indirect methods. We've seen that we can use Hess's law if we have the energy information of some related equations that we can use to get to our target in a different pathway. And we've looked at using heats of formation, in which we can use the heats of formation of the products and reactants of the reaction that we're looking for in order to find the overall thermochemical information for the entire reaction. Useful if we do know the heats of formation of all the compounds involved. And so this is the end of our discussion of thermochemistry. I will have another short lecture that sort of just ties a lot of this in together and wraps a lot of this up. Because actually this starts to represent the last of this unit as well. And so the last lecture that I give will sort of recap everything that we've done here in Unit 2, because it has been a lot. We've covered a lot of material, and so I will recap that for us for our next lecture. In the meantime, I hope everybody has a great day. Bye.